Okay, you guys hear me, right?
Yes, sir, we can hear you.
Okay, great. So let's see. Let's start working on worksheet number 3. Okay, here we go. Okay, so I guess we stopped last time. Hold on. Why is my tablet acting weird? Uh-huh. Okay, so we are using integrals in order to evaluate areas of shaded regions, right? Okay, it's better. Do you guys see my screen? I think it's a little bit lagging.
It's a little slow. It's still showing just like where you pulled up all the worksheets.
Yeah, otherwise. Mm-hmm. Okay, hold on. I don't know what's happening, but whenever I start this class, my annotator works weird. Hold on. Let me rejoin using my writing tablet. Oh, how did your exam go? I think the exam is due today. Have you guys taken it?
It was nothing like the practice exam. Only
Really?
it was only
They
a couple
us-
questions. It was
uh,
like I was like, what the heck?
well, usually they make it very similar to the practice test to motivate you to answer practice tests in the future. So, but how was it? Was it difficult or what?
It wasn't difficult. It wasn't what I expected.
Oh, I see. Mhm. Now, can you guys see my screen? Okay, so I guess you can. All right, so we are working with using integrals in computing areas, and just a quick recap what we discussed last time. The first step is always to have a good idea of how the region looks like, how the shaded region looks like. So that requires you to sketch the graph of the functions that are used to bound the region. So for instance, you are done sketching the graph. Your graph looks like something like what I have on the screen. You want to find the area of the shaded region, and if you were told or if you decided to use vertical strips, then vertical strips, remember, always come with a variable x. This will also be useful for computing volumes. Always remember, vertical strips, you use dx, right? And then once you knew that you will have an integral with respect to x, you need to find the bounds for x. What are the x values that are being covered by the region? Well, from the illustration, the region starts when x equals a and ends at x equals b. So my bounds for the integrals are a and b respectively. And then the integrand would be the height of the vertical strip. So it will be computed as the top function minus the bottom function. All right. Now, there are some moments wherein you might want to use horizontal strips. Now, whenever you are using horizontal strips, always the variable is y. So you put a dy into your integral to remind you that the next step is to find the bounds for y. What is the y value where the region starts and what's the y value when it ends, right? So in this particular graph I have on the screen, the region started when y is equal to c and ends when y is equal to d. That's why I have these two guys as the bounds, and then the integrand would be the width of the shaded region. How do you compute the width of the shaded region? Or sorry, not the shaded region, but the width of the horizontal strip. It would be the right function minus the function on the left. So right minus left, that's the integrand. But remember, you are supposed to integrate with respect to y. So the integrand should have the variable y in it. So if the function is given as y equals f of x, you need to compute for x in terms of y. So that your variable in the two functions involved would be all given in terms of y. Okay? And I guess we have done an example last time. featuring this obscure looking triangle. And we found the area to be 1/2. And then I guess we started answering problem number 2. It's just that at the back of our, well, at least for me, y equals 5x minus x cubed is not an easy cubic function. It's nothing like y equals x cubed. And remember, I need to have a good idea of how the graph looks like. So that compelled me to use techniques from curve sketching you learned in Calculus 1 in order to sketch the graph, so that I will have a good picture of how this function behaves over the real number line. So if you, I guess I solved the first part with you guys, compute for f prime. I wanted to compute f prime so I know if the function is increasing or decreasing, and then what are the local minimum and the local maximum. And I guess we discussed that last time. Then I went on ahead and look at f double prime, because f double prime tells me when is the function concave up or concave down. And then using these two information together, which again, hopefully you remember from Cal 1, will give me the sketch of this region. Okay? And we were told to find the area of the region bounded by the two curves. When we say bounded, we mean totally enclosed by those two graphs. So in this particular case, my shaded region would be this plus this, right? Because there are two totally bounded, totally enclosed regions by those two graphs, right? Well, this is not counted. This portion is not counted as part of the shaded region because it is not bounded, because this will go on forever, right? So it's not totally enclosed by those two graphs, as well as this one. This portion should not be part of the shaded region because it's not totally bounded or totally enclosed by the two curves, right? So it's an unbounded region because it goes on forever downward, okay? So that means I only have to worry about these two parts over here. And here, I'll decide to use I'll use vertical strips. And I will tell you later why using horizontal strips will be problematic for this example. So if I will use vertical strips, so I'm going to draw a test strip over here. And I observed that the top function is the blue one and the bottom function is the red one. However, if I imagine the vertical strip to be drawn somewhere to the right, like somewhere here, the behavior, the dynamics between the two functions change, because now at this vertical strip, the upper function is the red one and the lower function is the blue one. So that tells me I cannot just compute the area using a single integral, because remember the integrand is top minus bottom. But in this particular case, there are two subregions wherein the top and the bottom functions are different, right? So that tells me I need to split the integral up, compute the first area here, let's call it area 1, and then compute for the second area, area 2 there, right? Because in area 1, top is blue, bottom is red, and it's the other way around for area 2, right? And then, so though I am decided to use vertical strip, so we have encountered a problem here. And then another thing is that we need the bounds for x. When does the region start and when does it end? So it will start here, right? And it will end over here. But again, we need to split the integral somewhere here in the middle, right? So we need to look for the points of intersection of the two graphs to find those important points. Actually, we need 3 points. Those 3 points of intersection tells us the starting point for the region, the ending point for the region, and this crucial point where the top and the bottom function changes, right? So let's see, though it's a little bit obvious that according to my graph, this is x equals 0, right? And let's verify that that indeed is true. I need to solve for the second step after sketching the graph. I need to solve for the points of intersection. Okay. Now, how do you solve for the points of intersection? Well, you just need to equate the two functions together. So the first function is y equals x, the other function is y equals 5x minus x cubed, I'll just put them equal to each other. And to find what is the x value where their y values coincide, all right? So here I'll collect all terms to the left-hand side. So I'll have x cubed, and then I'll have negative 4x equals 0, right? And then I factor x out of the left side. So I'll have x squared minus 4 equals 0. That tells us that x is either 0 or x squared minus 4 is equal to 0. And then I solve for this one. I'll see that x is equal to plus or minus 2. Okay. So this tells me, okay, the graph starts at negative 2, or the region starts at negative 2. It will end at x equals 2. And then this other point of intersection, where the top and the bottom function changes role, is given by x equals 0. Okay, so that means area 1 can be computed as an integral from negative 2 to 0, and area 2 can be computed as the integral from 0 to 2. Okay, let's put that into writing. So here I will use vertical strips, and that's why the area is in terms of x. And we know there would be two parts to it. I'll put the x there. And then bounds for x. For area 1, the bounds would be from negative 2 until this point of intersection 0. Because from negative 2 to 0, top function is blue, the bottom function is red. So it's red minus blue. So it's going to be x minus 5x minus x cubed. So be careful with the minuend. Here, don't forget the grouping symbol so that you won't miss distributing the negative sign to both terms in the subtrahend. Okay? And then conversely, from 0 to 2, that's area 2. In area 2, top function is the red one, bottom function is the blue one. So that means we will have as integrand 5x minus x cubed minus the bottom function, x, with respect to x. Okay? And then all you need to do is to do the integration, carry out the integration. I guess it's straightforward. I will skip some of the details and just give you the final answers here. It's going to be 4 plus 4, and the area is equal to 8. Okay? Does that make sense, guys?
Yes, for me it does.
Thank you for letting me know. How about the others? You're quite quiet you're a bit quiet in the chat. I
had a question.
Oh, go ahead.
Why can't we use symmetry for this one?
Good question. Well, it appears that we can indeed use symmetry because here, I know the final answers gave me the area 1 is 4, area 2 is equal to 4. But unfortunately, I want to be, not unfortunately, but I want to be careful in using symmetry because at least according to my graph, I'm not sure if it's symmetric at all. But yeah, if you know the dynamics or if you have an idea about the symmetry of the function, then it's fine to use symmetry. It's just that for this particular example, I am not sure that area 1 is symmetric to area 2. Because why? Because the first function, y equals 5x minus x cubed, is a bit complicated for me, and I'm not sure, and I don't remember from algebra the symmetric properties of that function. But if you are sure, and you know for certain that your function is symmetric, then you can go ahead and apply and take advantage of the property of symmetry. I guess you're referring to just computing, say, the area of area 1 and then multiply the answer by 2. You can do that provided you are sure that indeed the two regions are symmetric. For this particular example, I'm not sure if they are symmetric, though it turns out they are. But if I am to do this, I would like to be very careful and not rely on visual inspection. I would have done an algebraic test in order to make sure they are symmetric. But since that is not the concern of this class, I decided to just forget about symmetry because I'm not sure about it at all and just use concepts in calculus to answer this. But for simple functions like y equals x squared or y equals x cubed, we know there is some sort of symmetry around x equals 0, and then you are free to use that. So use symmetry, take advantage of it if you are sure of it, but otherwise do it carefully. All right. Well, Faiza, that's a good question, and that's what I'm going to discuss next. So this in this particular problem, vertical strips is more convenient because I just needed to split the integral into two pieces. Because again, the dynamics is top minus bottom, right? But if you insist on using horizontal strips here, let me show you why it is complicated. Because here, if I draw a horizontal strip here, I hope you are seeing the green line I'm drawing. This horizontal strip will have the red function minus the red function. But unfortunately, that will not cancel each other out, because if you will solve for x in terms of y, you will have an equation for this part of the red function and another different expression, slightly different expression for the left part of the red function. So that means for some interval, you will have a red minus red, okay? And then if you go a little bit higher, say somewhere here, right minus left, so you will have red minus blue. If you go here, you have blue minus red. And then here you have red minus red again. So if you will insist on using horizontal strips, then you will need 4 integrals in order to solve this problem, right? Compared to what we just needed when solving it using vertical strips, you only needed to split the integral twice. But horizontal strips will require us to split it 4 times. Okay. Sometimes they are equally convenient to use either the vertical and horizontal strips, but sometimes it's quite hard, just as like what we saw in this example. And another consideration is the integral. If you're just to set up the integral, then it's fine. I mean, when you don't need to evaluate the actual definite integral, then it's good. You need to set it up. But sometimes when you set up the integral, either a dx or a dy will give you a very problematic integrand. So that's another consideration, not just how many splitting of the region you need, but also how the integrand looks like. Because if the integrand looks very complicated with respect to x, then try with respect to y. And that might be easier to evaluate. Okay. So yeah, so there are several considerations on what to use, but if you will be able to set up and compute them using both, you should get the same final answer. It's just the level of difficulty that is required to evaluate those integrals, right? But that's a good question though, yeah. Any other concerns? All right, so if none, let me go to some examples from the worksheet. So let me see. Okay, let's try example 4. Okay, so for example 4 in the worksheet, we have 2 functions. Hold on, let me pull up, just double check. Okay, example 4, the 2 functions are the following: y equals 2 root x, y equals 4, and we're told to bound it by the y-axis as well. Okay. Again, the first step is to sketch the region. Okay. At least obtain a good idea of how the region looks like. The main point here is we need the points of intersection and to know what is the function on top or at the bottom, right? So here y equals, I'll start with y equals 2 root x. When I know that this is a semi-parabola opening to the right. So when x is equal to 0, y is 0. And when x is equal to 2, when x is equal to, what do I want? When x is equal to 4, then y is equal to 4. Okay, and it's a semi-parabola opening to the right. So that's the graph of y equals 2 root x. And then the other function is y equals 4. So that is just the line y equals 4. Right? And we were told that the region R is the region bounded by these two graphs and the y-axis. The y-axis over here, so the shaded region should be this. Okay, so that's the region R. Okay. And here, we are lucky that we don't need algebraic calculations to find the points of intersection. We know here that this is x equals 0. And then here we know that it's x equals 4, and that's y equals 4 as well. So those are the important points that we have. All right. Now, the next is, though we don't need to solve for the points of intersection, so I'll skip that part. Then let's set up the integral. Then again, we have two options. So first, I can use vertical strips. So whenever I'm using vertical strips, I have an integral with respect to x. And then now I need to bound the x. So what is the starting x value? Starting x value is 0. Ending x value for the region is 4. Right? So that's why I have those bounds. And then the integrand would be the height of a vertical strip. And the height of the vertical strip is computed as the top function minus the lower function. So the top function here is y equals 4. So we have 4 minus the lower function 2 root x. All right. Now you could also try using horizontal strips here. I don't think it is very complicated to do that. Well, let's observe how a horizontal strip look like. So a horizontal strip will look like this, right? And if we slide this horizontal strip up and down the region, we observe that the right function is always the red one, and the left function is always the y-axis, right? So no matter where we draw the horizontal strip, it's always the red curve and the y-axis on the left. Okay, so that means it's fine. There's no big issue in using horizontal strips here. Now, horizontal strips always go with dy. And then since I have a dy, I need to bound the y. So I look for the y values where the regions start and when it ends. So it will start when y is equal to 0, and it ends when y is equal to 4. It's just a coincidence that the bounds for x are also the bounds for y. Most of the times they would be different from each other. Okay. And then now we compute for the integrand, and the integrand is just the width of the shaded of the horizontal strip. Remember, it's going to be right function minus the left function. But take note, we are using integration with respect to y. So the integrand that we will place here should be expressed in terms of the y variable. So remember, we know that the red function will be involved, but we cannot use the variable x in the integrand. So for this case, I need to solve for x in terms of y. So in order to do so, I need to square both sides. I'll have y squared equals 4x, right? And then divide both sides by 4. I'll have this, or equivalently x equals y squared over 4. So in terms of y, the red function is x equals y squared over 4. And that's the right function. So that would be the minuend here. Minus the left function. What is the left function? The left function is the y-axis. What's the equation of the y-axis? The y-axis as equation, what? Do you guys remember?
0.
Right, it's x equals 0. So the minuend here is 0. Okay. And then if you are patient enough to calculate these two integrals, they will both give you 16 over 3. So it shows us that it doesn't matter what type of strip you use, you will end up with the same answer. And both of them are not that difficult at all, though the one using horizontal strips might look a little bit easier to the eyes insofar as integration is concerned, because it's just a polynomial. Here you have a square root function, but integrating it is not a big deal either. So if you're given the choice, then you can choose which one is more convenient to you. All right. Okay. Any questions on that? Is that clear? Okay, I'll take your silence as a yes, or a silence of type 1. Ready to proceed to the next problem?
Yes.
Let me see. I'm trying to pick one that's interesting. Okay, maybe let's try problem 7. So for problem 7, the region is bounded by y equals 4 minus 3x, y equals e to the x over the interval -1 to 0. Sometimes you will be given regions like this, wherein the two functions that will be given are not enough to produce a totally enclosed region. So sometimes there's an additional constraint given, like x's being over some interval. For instance, here our interval is -1 to 0. But nevertheless, let's proceed with the step 1. We sketch the graph, or sketch the region, by plotting the graphs. So here, I'll start with sketching the straight line. So for the straight line, y equals 4 minus 3x. I'll start plugging in two numbers I want. Oh, but remember, we are interested only on the interval -1 to 0. So might as well give those two values for x. When x is equal to -1, then y would be what? -1, this would be 7. So 7, somewhere here. And then when x is 0, we get y equals 4. So the graph over the interval -1 to 0 is something like this. Okay, so that's a straight line. The second one, the second function is the exponential function. Y equals e raised to x. When x is -1, then y is 1 over e, right? Or e to the -1. But e is 2 point something, so this would be less than 1. So let's put it somewhere here. E to the -1. Put it here. But when x is equal to 0, then y is equal to e to the 0, which is 1. So it's somewhere above that. And it's a curve, right? So if you want to sketch the bigger picture, so it looks like that. Right? But remember, we were told to just find the area for x's between -1 and 0. So that means the shaded region is just this one. Okay. Now, next decision to make. Since the problem didn't tell us what type of strips to use, we are free to use the more convenient one, right? What do you think is the more convenient one? Horizontal or vertical strips?
Vertical. We're already given the equation.
Right, so vertical strips, because we are given the equation. And another thing is that if you use vertical strips, so you draw a test vertical strip, you move it to the left or to the right, the red function is always on top and the blue function is always at the bottom. So that tells us we can evaluate this using only an integral. If you will insist on using horizontal strips, then you will have to split the integral into 3 pieces. So the first piece is over here. Maybe I should change the color here. This one, call that green, right? So you need to split it into 3 pieces. One is because here the right is the blue minus green. Here you will have, well, let me use black here. You will have black minus green, and then over here you will have red minus green. So if you will use horizontal strips here, you will need to split the integral into 3. And not just that, you need to solve for x in terms of y, which will entail a lot of work. And definitely using horizontal strips is a much simpler way of answering this problem, right? I don't need to compute for the points of intersection because I know what the bounds are exactly. So I'll skip that step and just go ahead and give the integral. Now, again, we decided vertical strips are much more convenient, so I have a dx there. And then what are the bounds for x? The region starts when x is -1, and it ends when x is equal to 0. So those are my bounds here. And then it's top minus bottom. The top function is the red one, which is the line. So I'll have 4 minus 3x minus the bottom function is the blue one, which is the exponential function. Okay. And I don't think it's hard to integrate this one. So I'll leave the integration to you guys. And I guess the answer for the region is 9/2, or for the area of the region is 9/2 plus e to the -1, whatever that value is, right? So you're not allowed to use calculators during exams, so you can keep your final answer like this. You don't need the approximation to e to the -1. Okay. Any questions on that one?
I kind of forgot how to integrate e to the x when there's something in the exponent, so I was wondering if we could go over that.
Oh yeah, sure. Basically here, this will just be, the integral would be 4x minus 3x squared all over 2. It's e to the x dx, and exponential functions have a very nice property. The derivative of e to the x is itself. Therefore, the derivative, the integral of e to the x is also itself. So you'll have e to the x as well here. Then you evaluate it from -1 to 0. And then when you evaluate that, plug in 0 minus plug in -1, you'll get this. Okay?
Oh, I meant when there's something in the exponent, like say it's like e to the 4x or something like that.
Okay. Yeah. So if you have an integral of e to the 4x dx, so you will need to use u sub. So you let u to be equal to 4x, du is 4 dx, and then that means dx is d over 4. So this would be 1/4 e to the u du. And that's 1/4 e to the 4x plus the arbitrary constant c. Right. So you need a u sub there.
Thank you. I was so
All right.
confused and I was so afraid to ask her that.
No problem. This is a safe space, guys. You can ask your questions freely without any judgment. Okay, other questions? Oh, I heard that you already finished section 7.4 from the lecture. Is that correct? Sorry. So I'm thinking, you're not yet done with section 7.4? Because, you mean the first part is volumes of solids where you are given the cross section. But you haven't gone through solid suprevolutions yet. Okay, great. So that means we can spend a little bit more time on areas, and then we start with the remainder of with those topics from 7.4 on Monday. That is, if you still need some more examples about shaded areas of regions. But if not, I'll be happy to go ahead with volumes. So what do you think, guys? More examples about areas, or let's go ahead for volumes? Okay, more examples then. Let's see, looking at the problems in the worksheet, what would be interesting? Okay, maybe let's try this. Let's try number 5. Did I do number 5? Not yet. Yeah, let's do number 5. So for number 5, the functions are this, or the region is bounded by y equals x cubed and y equals 4 root of 2x. Okay, all right. So first step, sketch the graph. So this will require you to read a bit on your pre-calculus or algebra or Cal 1 notes. So make sure you at least remember how to sketch those basic graphs. Because otherwise there's a big chance that you will miss the right integral for the area, because you need to identify what goes on top and what is at the bottom of the region, right? So y equals x cubed, I know it's a the basic cubic function, so I don't need any fancy technique in order to sketch its graph. So I know that that's something like this, right? And then y equals 4 2x. So maybe here, this is a semi-parabola opening to the right. So I can give just some specific points on that. So if I have, change pens. If I have y equals 4 root of 2x, and then if I will let x is equal to 0, then y equals 0, 2. So I'll have that. And that's a lucky thing, because I know the first point of intersection is 0, 0. And then probably I'll pick what? I'll pick x equals 2. If x is equal to 2, then y is equal to 8. 2, then y is equal to 8. But actually, they will intersect somewhere there. So
They intersected too.
Right. And actually, that's why I chose x equals 2. But in case you were not able to clearly see that, then you can solve for the points of intersection as your next step. And again, all you need to do here is to put the two equations or the two functions equal to each other. So the first function is, I forgot to write it here, y equals 4 root of 2x. So the first function is x cubed. The other function is 4 root of 2x. You solve for the POI just in case you didn't see it graphically. Or if you just want to make sure that you indeed have the right points of intersection, then solve for them algebraically. So I can square both sides of the equation to get rid of the square root. So I'll have x to the 6th equals 16 times 2x, and that's 32x. And then I collect everything to the left side. So I'll have x to the 6th minus 32x equals 0. I'll factor out the x. X to the 5th minus 32 equals 0. And this means that either x is 0 or x to the 5th minus 32 is 0, but that means x to the 5th is 32, and that means x is equal to 2. So indeed, we have the right x values. So, and what are the corresponding y values for the points of intersection? Well, if x is 0, then y is equal to 0. And then if x is equal to 2, then y is equal to 8. And exactly that's what I found out in sketching the graph. And then remember, the region is the region that is bounded by these two curves. So the region is this one, right? The highlighted portion. And if I will use vertical strips, I'm perfectly fine, because anywhere I draw that vertical strip within the region, the blue function is always on top. The bottom, the red function is always at the bottom. So that means I don't need to split the integral up. So in this particular case, I have area using vertical strips. Area is in terms of x, and then the bounds would be bounds for x. But if you go back to the region, we know that the region started here at x equals 0 and ended when x is equal to 2. So the bounds are from 0 to 2 of the the square root function, 4 root 2x minus the cubic function, x cubed. And then when you calculate this integral, Robert is right, you will get 20 over 3. Okay. Now let's try if horizontal strips would be as convenient as that. If we draw a horizontal strip and imagine it being slid up and down the region, the red function is always on the right and the blue function is always on the left, right? So it seems that it's also convenient to use horizontal strips, right? But the problem with using horizontal strips is that it would go with a dy, and then the integrand should be expressed in terms of y. So we cannot use the function at their current forms. So remember, the red function is y equals x cubed. If I want to use horizontal strips, I need to solve for x in terms of y. But that's not a big deal. This is equivalent to saying that x is equal to cube root of y, right? You just took the cube root of both sides in order to get the value for x. And then the other function was y equals 4 root of 2x. Then we solve for x in terms of y. We square both sides to get rid of the square root. So we get 32x again. And then we divide both sides by 32 in order to get x equals y squared over 32, right? And they will serve in the integrand for the area of the region, okay? So again, if you are using horizontal strips, you will use dy as your variable, and then we need the bounds for y. If you look back at the region started when y is equal to 0, and it ended when y is equal to 8. Remember, I'm bounding y. So y values go in the limits or in the bounds of the integral. So it would be from 0 to 8 of the right function. What's the right function? The right is the red one, the cubic one. So we'll have cube root of y minus the left function y squared over 32. And if you calculate this integral, you will also get 20 over 3. The same answer as what we get using vertical strips. Okay, so that tells us it really doesn't matter what type of strip you use. Sometimes they are equally convenient, but sometimes one is more convenient than the other. All right, let's see. Any questions so far? Or any, do you foresee any difficulty with this topic? Okay, it seems everything is clear. Let's have another one. Any particular problem that you think is interesting among those in the worksheet? Probably let's try problem number 9. For problem number 9, we were given the function in terms of y. So for problem number 9, we were told that the region is bounded by f of y equals negative y squared plus 1 and x equals 2y plus 1. Okay, so let's try to have a good idea of how the graph of these two guys, of these two functions look like, right? So basically here, oops. Okay, x-axis, y-axis. The first function is or has a quadratic term in y. So that means it's a parabola opening either to the right or to the left. And since y squared has a negative coefficient, then this is a parabola that opens to the left. And the vertex occurs when y is equal to 0. When y is equal to 0, x will be 1. Right, so maybe I should put that here. I have x equals negative y squared plus 1. That's the first function. This is a parabola opening to the left. Actually, it's not technically a function of y, but a relation in y to the left. Okay, that should remind you of your conic sections. But here, if y is zero, then x is equal to 1. And then if you set y equals plus or minus 1, then what? We get x equals 0, right? So y is -1, y is +1. We both get x equals 0. So the graph will look like this. Okay. So that's the graph of x equals -y² plus 1. Okay. And then let's draw the line. It's a line in y, but that's perfectly fine. Just give arbitrary values that you want for y. If y is equal to 0, then maybe I should write that down here. X equals 2y plus 1. If I choose y to be equal to 0, then x is equal to 1. And luckily, that's one of the points of intersection, right? Then another is if I let if I let y to be equal to any number that you like, actually. If y is -1, then what do we have as x? X would be -2 plus 1. That will be equal to -1. Oh, I'm lucky that that's another point of intersection. Sorry, not I thought it would be a point of intersection, but it won't be. So y is -1, x is -1, it will be here. Yeah. Oops, not necessarily a point of intersection, but isn't really a point of intersection. Y is -1. Yeah. So the graph looks like this. Okay, so that would be the shaded region. This would be the two graphs, and the shaded region would be somewhere here. Okay. Now let's try, since the functions are given in terms of y, then maybe a good start is to use horizontal strips. Again, the functions are given readily in terms of y, and the horizontal strips require a dy. So that's why I'm starting with a horizontal strip here. So using horizontal strips, we get what? So using horizontal strips, the area would be with respect to y, okay? And then y value starts where? Actually, we need an additional step here because we don't know when the y value will start. It is not clear if it will really start at y equals -1. Perhaps it will start earlier, right? Or yeah, it will start earlier. So I forgot the next step. Since it's not clear what are the points of intersection, then I need to solve for them, right? So here we solve for the POI. But remember, the two equations are x equals -y² plus 1 and x equals 2y plus 1. So we make them, we set them equal to each other and then solve for y in terms of x. I'll collect them all to one side. So I'll have y² plus 2y equals 0. And then factor out y. And then this means y equals 0 or y plus 2 equals 0, signaling y equals -2. So my hunch is correct that it won't start at -1. It will actually start here where y is equal to -2. Okay. So that means here my bounds would be starting from starting from -2 until 0 of what is the right function? The right function, or the function on the right, is the red graph, which is of the parabola. So that will be -y² plus 1 minus the left function, which is the blue one, which is the line to y plus 1. Just remember, be careful with the grouping symbols. The entire second function, or the entire left function, must be enclosed in parentheses, again, so that you won't forget to distribute the minus sign when you evaluate the integral. All right. Then if you perform the integrals here, the integration here, you will get 4/3. Now, do you think there would be a big issue if we have used horizontal strips instead? If you use vertical strips instead? Well, graphically, I don't think there's a big issue because, okay, a vertical strip, top function is always the blue one, bottom function is always the red one. But the only difficulty there is that the functions are given in terms of y. So if we insist on using vertical strips, we need to solve for x in terms of y. And though that is not that difficult in this case, because for instance here, we will see that that y is equal to what would be x in terms of y. I will have y equals plus or minus the root of 1 minus x, and the line from here, x equals 2y plus 1, we can solve for y in terms of x to get y equals x minus 1 all over 2. So kindly check, probably as your homework or something to do when you're bored at home. If you use vertical strips, then the integral should be from -3 to 1 of x minus 1 over 2 minus negative root of 1 minus x dx. And if you evaluate that, that will also give you 4/3. Okay. So try to come come up with the same integral, and then let me know on Monday if you have some questions or difficulties with it. And yeah, and then if you don't have any other questions about using integrals in computing areas, then we can start Monday by solving examples from 7.4, still at worksheet number 3. But don't worry, guys. I guess there is still a bunch of problems that I haven't from worksheet number 3 that we haven't solved yet. What I'll do is to include the answers to those problems in the annotated worksheet that I will upload later today. Is that okay? And then you just let me know on Monday if you have some questions with some of those problems, all right? So yeah, so I suggest go over the problems that we didn't tackle here in the lab. And then once you have your answers for them, you can go to the annotated worksheet later this afternoon and compare your answers with mine. And if you got something wrong, try to deduce what went wrong or what is the right way of doing it. Try to discover it on your own. But if you're not able to find it on your own, let me know on Monday, and I will be happy to help you with your questions. All right? Does that sound good? Hello, guys. Are you still there? Okay, so if that is so, then let's call it a day today. So I hope you guys have a good weekend ahead. Good luck on the exams. Thank you for coming, and see you on Monday again. Bye, everybody.